Welcome back. I'm glad to see you again. In previous lessons, we have looked at how to train machine learning models, how to get the data, featureize it, and also modify the machine learning models and do predictions. In the remaining part of this course, what we'll try to do is wrap up with some know-hows of machine learning. In this lesson, we'll look at pre-trained models and how you can use the models that have already been trained by others and make predictions, and also use those pre-trained models to do something called transfer learning. Let's dive into the code. So there are many machine learning models out there which people have trained and the weights have been optimized. And if you want to use some of those models, this lesson will show you how to do that. Over here, what we are going to do is use a graph neural network that is published in this article, and the property that the model predicts is the lowest singlet excitation energy, and that excitation energy usually corresponds to the absorption maxima of the molecule. So if you want to read more about that, you can click on this article link, and the article is available for free to read. So at first we'll download the model, and what is critical in the model is the model parameters, the init function, so whatever parameters that you put in to create the model, and then the optimized weights. So the first one that we are going to download here is the model itself, and that is the weights, and then parameters are the parameters for the model. So it'll download it, and once it's downloaded, you can click on this folder icon over here, and you'll see we have best r2 and parameters.json. And once this is here, you can proceed further to load the model and do predictions. So this model is a graph neural network, so we'll install DGL, DGL Live, and RDKit to do the processing. And while that is being loaded, let's look at the code here. And this code is let's run it again. So this code is for the MPNN used in the article. It's a message passing neural network, and this is pretty much similar to what we have been doing before in the graph neural networks. We have an init function and a forward function, but this has something to do with concatenating features that we talked about in modifying neural networks, and this is what it looks like. Okay, so we need node input features, edge input features, and all the other parameters are usually set, but we do have the parameters.json file which we can use to create this model. So let's run this code and make sure our class for the model is ready to go. It's importing, and okay, once it's done, we'll get the model parameters. As I mentioned before, the model parameters are parameter.json file, and we'll see what the parameters are. So we have the dropout, the hidden features, the node out features, all that is required for training the model or making predictions. And this is not usually available like a parameters.json. It depends on who creates the models and how they make the parameters available. You may find this in the supporting information of the article that reports it, or if the authors are more willing to share the code, you can find something like this, or configure.json or configure or something which gives you those parameters. And if you look at these things, we have most of the parameters except the node in features and the bond in features or the edge in features. So we would need to add that. And if you remember from the canonical atom featureizer and bond atom featureizer, the ones that are used in this model, and also the ones these are the ones that we have discussed before in this course, and the features are 70, node features are 74, and edge features are 12. So let's add that to this dictionary, and parameters.update updates the dictionary that you see up here. And once that is ready, we can pass in the model parameters. There's no need of explicitly typing in all these values. So this is one way of passing keyword arguments. So you put into asterisks followed by the parameters, it's the dictionary. It'll automatically know what to set where, and then you see the in features are 74, and then the bond features are 12 for this. So this is the model. We have GNN layer, readout layer, predict layer, and predict layer looks like this. We have a dropout layer, linear function, a value followed by batch normalization, and then an output. So this is pretty much standard looking. So now what we need is the weights for these models. The parameters and everything is set over here, and what the model training actually does is optimize the weights. And if someone gives you the optimized weights, there's no need for training the model. You can just use the model. And the way we do it is loading the model weights, and this is how it is done. So we have load state dictionary, and this is where it gives all the mapping and parameters that are required, the weights, and we say okay, torch.load, we load this model. The reason we are giving map location torch.cpu is because we have been training for so long on CPU. The lessons that would follow would show how to train the model on GPU too, but as this model is on CPU, we do mention that it's mapped to CPU, or else the model would not load, it'll give you an error. So once we click on that, it'll always output all keys match successfully. This means that the weights that are here and the model that was created up in this cell are matching, and that's pretty good. If suppose we did not have the in features right or the out features right, it would give us an error that they don't match. You can try it and put in some different node in features or edge in features, and can put in some node in features or edge in features and see whether that thing changes. So once it is loaded, we have that all keys matched. Now what we need to do is put in a smiles representation, which is converted into a graph for learning, for prediction, and look at how it performs. So over here what we are going to first do is load all the canonical features, atomizer, canonical bond, and atom featureizer, and we have that in place. So as an example, we'll do ethane and not the entire data set of QM9 or anything. So we'll use ethane and we'll convert it into a graph as we did before. So, and this should display a graph object which has two nodes and two edges because it's bidirectional graph. Once we have that, we can just make the predictions. So model.eval, make sure that this is set up right, and we have node features we get from HV, this ones, and HE, the edge features, we get that, and we pass it to the model, and it should make the prediction for us. And this is the predicted value, and this predicted value corresponds to the singlet energy, S0, S1, I think, and this is 4.25 electron volts for ethane. And you can try to change the smiles up here and then load another graph and see what it predicts. But this is how we can make predictions on models that are already trained. All you need to do is just make sure you have the parameters right for creating the model, and then load the weights, and those will be sufficient to make predictions. Now, some of you may ask, okay, how do we save the model that we have already trained in previous lessons? And there's one line that you need to do is, once you have a model that is trained, all you need to do is model.stateDict, and is what you want to save. This is the state dictionary that we loaded up in a couple of cells above, and we can see that we loaded the state dictionary here. So we need to save the state dictionary. So that's what we are doing. So we are going to use torch.save function, pass the model state dictionary. Once that is passed, you give it a name, and let's say the model that was here, we give it a name, my torch model. And once that is saved, you should be able to see my model.pt, which is the model that saved you. For saving the weights, you need to find some for saving the parameters, you may need to find some way to tell what parameters you have used where and what are the model parameters, and that's usually a JSON or something that you create so that all those things pass in to the information as to how to create the model first. And the model, the PT that you saved over here, is just the weights part of the model. So we know how to save a model that you have already trained and how to load a model that was already saved from somewhere or you got it from someone else. But that's not the only thing that we can do with the models that are available. There's also this transfer learning which people use, and this is something that helps speed up training or help you in cases where you have limited data. What you can do is use the model that is already trained on large data and just modify the few output layers and see how the predictions go. So for example, let's say you have a HOMO-LUMO gap model trained on the QM9 dataset, and if you want to now predict the HOMO energies of the molecules, not the HOMO-LUMO gap, there's no need of starting a model from scratch and then training the model. What you could do is, let's say we have a graph neural network, we freeze the GNN layer, the readout layer, and don't change the weights for those layers. And what we assume over here is whatever you put in there, the model already knows how to convert it to a representation for the predict layer to predict. So we assume that and say, okay, the HOMO energies, what needs to be changed is only the predict layer. Let's only change the weights of the predict layer for all the linear value and linear that you see within the predict part of it, and keep the others constant. So what happens is you have less number of parameters to train because you're only looking at the predict part of the model. So you have less number of parameters. So even if you have less data to train, it doesn't matter. It trains pretty well because you have less number of parameters to train. And it also saves time because only a small number of parameters are being trained. And the way to do this is what we'll look at in the code over here. So as I said, you have GNN part of it, you have readout and predict. So we'll keep the ones on the inside, the GNN and readout, fixed, but we just want to change the predict layer or make the predict layer more trainable and just fix the weights for the inner ones so that we don't have gradients calculated, and that's what it means. So we don't have any gradients calculated for the inner values, so the weights are not changed. So the gradient is 0 and there's no change in weights that we usually end up doing. So how do we do that in code is you look at the model.parameters, it will give you all the weights that are associated with this model. Okay, so these are all layers. This is a layer containing something, and it says these are the weights for the layer and all the neurons that you are using, and it says requires grad is equal to 2. So this means that gradient is calculated for this layer always. And if you can keep scrolling, you'll see a lot of weights, and these are the model parameters, the weights, and all of them have requires grad equal to 2 and requires grad equal to 2. What we need to do is requires grad equal to false for most of the layers, and to do that we'll just loop over the model parameters again and say param dot require grad. So param is just this tensor, and we say require grad is equal to false. What this does is it freezes all the weights, and if you look at the code again, now you don't see that required gradient equal to 2. So it is frozen. So this means that if you're going to train this model, use this model and train it with your data, the predictions are not going to improve at all, because the weights are not going to change, because there's no gradient associated with this. So you will just be stuck with a model that's not learning. But that's not what we want. We want to freeze the weights of the inner layers, the GNN and the readout layer, but not the predict layer. We allow the predict layer weights to change so that the predictions can be tuned to what we are trying to predict. The model maybe was trained for singlet energies over here, but we want to train it for homo-lumo gap. In that case, we just change the outer part and say, okay, let's not freeze everything. Let's keep the model.predict parameters. Let's let them say they should have the gradients, and we can check that again, and we should be able to see that some of the models require gradient. I think this is the bottom of the parameters, and they require gradient. That's okay, and that's what we need. But as we go up, we should see that that thing should disappear, because those models over here are from these layers are some of the inner layers, the GNN and the readout parts. So you should see the gradient being false for that, or not appearing anywhere. Let's see, yeah, there you go. So these weights will never change during model training, and we just keep it like that for these layers, but just change the outer layer for training. And if you want to use this model for the training now, just use the normal code that you have for training a model, and this will be just the model that you use, and model.train, it'll train the values, and normal loop of validation, train loader and validation loader should do the job for training. And this is immensely helpful if you have low data, and we have this freezing weights helps you to keep the number of parameters that need to be trained small, and speeds up training, and thus giving you better accuracy than starting from scratch.